So for today, we are going to solve this complex number question that is a generalization of what we have solved yesterday. So suppose p is a positive integer where w equals to e to the power of I 2 pi over p. We are asked to find the value of fp, which is defined to be the summation of 1 over 1 plus wk plus w2k, where k equals 1 to p minus 1. One interesting observation is that the value of fp depends on whether p is a multiple of 3 or p has a remainder of plus minus 1 when it divided by 3. Please have a good try before you add the answer.
Pause the video now if you wish to solve it. Keep watching the video once ready.
Now we try to solve a simple case. Let p is a multiple of 3. So call p equals to 3r for some positive integer r. Then we will see that 1 plus wr plus w2r, 1 plus w, that is e to the power of I 2 pi over p, that is 3r, then the whole thing power r, plus ei 2 pi over 3r, then power 2r. 1 plus wi 2 pi over 3 plus e to the power of I 4 pi over 3. Each of these terms is actually a solution for z power 3 equals to 1. Using the Vieta formula, the sum of the roots will equals to 0. Now, so for p equals to 3r, this summation runs from k equals 1 to p minus 1. For some instance, k will equal to r. But when k equals to r, 1 plus wr plus w2r will equal to 0. And therefore, fp is undefined if p equals to 3r. Okay. So what we need to do is we'll consider next p equals to 3r plus 1 or p equals to 3r minus 1. If you enjoyed this video, please like, comment and subscribe. For the remaining two cases, we need one more result to support it that we call it as a lemma. And this result is summation w to the power of 3k to the power of n, where k equals to 1 to p minus 1 will equals to negative 1, where the w is similar as what we defined, and the n has to be less than p, and 3n is not a multiple of p. So let's try to prove this result. And in fact, this summation form a geometric series. So summation w3k to the power of n, where n equals to 1 to p minus 1. It can be written as the summation w3n to the power of k, where k equals to 1 to p minus 1. When k equals to 1, the first term is w3n. When k equals to 2 is w3n squared, and so on and so forth. So the first term is w3n using the formula of sum of geometric series. It is w3n 1 minus the common ratio to the power of the number of terms, that is p minus 1, divided by 1 minus the common ratio w3n. This actually implies that wp is equals to e I 2 pi that is equals to 1. So this means that this is equals to W3N 1 minus, for this I can write as WP to the power of 3N multiplied with W negative 3N. And this is 1 minus W 3N. Okay, so when we multiply inside, this is W3N. This actually equals to 1, and this will equal to W3N times negative W3N, that is equals to 1. So it is W3N minus 1 over 1 minus W3N. So this is equals to negative 1. Okay, and therefore we have this result. Let me write the result here so that we can refer it later on. So the summation we need this because we do not want W3N equals to 1. And now we are ready to find the FP, where P equals to 3R plus 1 and P equals to 3R minus 1. So now case P equals to 3R plus 1. So the FP is actually equals to summation K equals to 1 to P equals to 3R minus 1, that is 3R. And this is 1 over 1 plus WK plus W2K. We use a technique that we have yesterday, that we multiply each of this by 1 minus WK. 1 minus WK. And note that 1 minus WK is never equals to 0. So this will give us summation K equals to 1 to 3R. And therefore this is 1 minus WK, and this is 1 minus W3K. Now this is crucial now, that W is equals to EI 2 pi over P, where P equals to 3R plus 1. So it means that W 3R plus 1 is equals to 1. So we take the power of both sides by 2K. This will be W 6RK plus 2K equals to 1. And we'll multiply this with WK, and we multiply this with WK. So it means that WK is actually equals to W combined together 3K to the power of 2R plus 1. So now we use this WK equals to W3K to the power of 2R plus 1. It is 1 minus W3K to the power of 2R plus 1. We can see that this term can be written as 1 plus W3K plus W3K square, and all the way to W3K to the power of 2R, where K equals to 1 to 3R. Okay, let me continue here. So the first one will be summation 1 from K equals to 1 to 3R. It will give me 3R. And for each of these, it is summation W3R to the power of some n. And this n is less than P, and 3n is not a multiple of Kp. So using this lemma, we know that the summation of each of these is equal to -1. So each of these is equal to a -1. And we have altogether 2 R terms. So this will mean that Fp will equal to R if P equals to 3R plus 1. So this solve for P equals to 3R plus 1. Next, we will do the similar thing for P equals to 3R minus 1. So when P equals to 3R minus 1, Fp will equals to the summation K equals to 1, and this become 3R minus 2. And again, for this, we already do it a few times. This will be 1 minus Wk over 1 minus W3k. We do the similar thing here. This will be equals to W 3R minus 1 equals to 1. So it means that W 3R equals to W, and therefore Wk is equals to Wk to the power of 3R, and therefore this equals to summation K equals to 1 to 3R minus 2, where this is 1 minus W 3k to the power of R. This can be written as W 3k to the power of R. Okay, and this is 1 minus W 3k. Again, it can be further simplified to have k equals 1 to 3R minus 2, and this is 1 plus W 3k, W 3k squared, and so on and so forth until W 3k R minus 1. So let me continue here. Summation 1, where k equals 1 to 3R minus 2, it will be equal to 3R minus 2. Summation W3k to the power of some power from 1 equals to 3R minus 2, it is actually equal to -1 based on the lemma just now. And it means that each of these will be equal to a -1, and we have a total of R minus 1. And therefore we have 3R minus R, that is 2R, and -2 plus 1 is -1. So this will be the result for P equals to 3R minus 1. So with this, we can conclude the following. That is, Fp will equals to R if P equals to 3R plus 1, and it is 2R minus 1 if P equals to 3R minus 1, and is undefined if P is a multiple of 3. And this conclusion that we have, and this end of today's discussion. I'll see you again next time. Bye bye.